Okay, welcome back. This next video is going to be about mechanical resonance, especially with regards to musical instruments. Resonance is something that is in not just in music, but it's just the response of all objects to some kind of periodic forces that can actually put an object into vibration. Um, Helicopters have to consider mechanical resonance. Race cars have to consider mechanical resonance. Most vehicles would have to consider mechanical resonance in their design, such that they don't end up shaking at very specific frequencies, because all objects have a natural frequency in which they would start to vibrate. I know sometimes when the big trucks drive by my house, if they have their muffler tuned a certain way and they rev their engines up a certain way, they can actually start to shake pictures that I have on the wall. And some houses, windows will start to vibrate a little bit when those types of large trucks drive by. So mechanical resonance isn't just something that is related to music. It is just the tendency for any object to vibrate when it's subject to a periodic force with the exact same frequency as the natural frequency of an object. Uh, a famous example of mechanical resonance that went wrong was the Tacoma Narrows Bridge back in 1941. It's worth looking up. The bridge just starts to shake and dance and fall apart. But I'll leave that to you to look up, or I might even put a link to it down below in the description section. But I won't play it here. So I've got two examples here, visual examples. On the right here, we have some acoustic guitar, and the guy put his camera phone into the acoustic guitar and just started hitting the strings. And you can see how when music is playing, the strings will actually vibrate. Now his phone is at one frame rate, and obviously this is going to pick up, and it's at slow-mo, and so it's going to pick up the actual resonance of the strings vibrating. So as you can see, they have different wavelengths as they vibrate, so that would be related to different sounds, different pitches that you'd actually hear. On the left is a glass that is in the presence of a tone that is the same as its, of course, natural frequency, and so it's causing the glass to vibrate. Now this is under a strobe light, so the vibration can be picked up. I'll show you an example of this in class when you're actually in class. You might have to remind me, but I will show you an example of this in class, of what it looks like for something like this to vibrate under a strobe light. Now, some people can do this with their voice when they sing. If they hit that exact frequency and their voice has enough intensity when they're singing, the glass will actually break. I believe Mythbusters were the first ones to actually catch this on camera, somebody actually breaking glass. At the very least, that's what they said, so I'll take their word for it. Maybe they're wrong, maybe I heard otherwise. I'm not going to verify that. I heard that, that's what I'm going with. So if this thing shakes any more than this, it will snap, because glass is not overly ductile or malleable for that matter. So types of string instruments that undergo mechanical resonance. We've got ourselves a piano. It is a string instrument, even though you're hitting these keys over here. They're attached to a mallet, and the mallet hits the string, and that's what gives you the sound of a piano. And there are many different types of string instruments that are like guitars. Guitar tends to be the default string instrument that most people think of. Obviously, there's also the harp. You'll probably see them a lot more in weddings. Acoustic guitar, you got your violin, your banjo, and then mandolins, and a whole bunch of other instruments that I just don't know the name of all of them. Obviously, I could zoom in and look at each of these, but I'm not going to. So these are all string instruments. They all have a certain way of causing the string to vibrate. Typically, you can either use, like a violin, you can use another stick to rub against the strings, and it'll cause a certain tone that, you know, is appealing if you like the fiddle. But I'm not going to get into all the individual types of instruments. They're all string instruments. So when it comes to a string that vibrates, we did this in class at some point with a slinky and a long coiled spring, where we just shake them back and forth in our slinky lab. So here we have the example of the standing wave. So in the standing wave, you ended up with creating a wave, a pulse, a series of pulses that would send that you sent along down to your partner, and it moved typically in one direction. When it got to the other end, it reflected back. Now, if you're able to do this with your hand steady enough, you were able to make it so that there was a part of the wave, specifically where the nodes are, where at all points the wave was just canceling itself out. A crest was overlapping with a trough, and you ended up with destructive interference to the point where absolutely no movement was happening. So if you're doing this by hand, odds are good it was hard to keep that actually steady, always setting the same frequency of the wave. And odds are good if you did this in real life, you'd probably see this node bounce back and forth in different spots. It wouldn't bounce around too much, but that's again because your arm would probably get tired, or it's just really hard to actually be consistent by hand. If you attach it to any kind of mechanical system where you can just set it as a frequency, this little pink spot right here, the node there, the node there, the node, all the points to the left there, to the right there, they wouldn't move whatsoever. All right, and I will demonstrate this in class on one of the days where you're in the room. So this, by definition, is a standing wave. And they call it a standing wave because you don't actually see the waveform travel to the right or travel to the left. All the movement is just occurring in simple little spots where you have the constructive and destructive interference happening at the antinodes. So that's where all the movement is going. Halfway between each of the antinodes is the nodes, and that's where you're always going to have destructive interference. The wave is just going to cancel itself out at all points. So those are the main parts of the standing waveform. And that's the fundamental idea when it comes to resonance, especially with string instruments. So the lowest any vibration that a string will undertake when it's undertaking resonance is known as the fundamental mode. So that means if you fix it at both ends, I'll put pink on both sides, so that's where the two nodes are. So all the vibration is going to look like just a game of skip rope as it goes back and forth, back and forth, back and forth. And the length of this instrument, so we'll call it L. There we go. So whatever that length is from that point all the way to that point, so that would be the length of the instrument. And as you can see here, at any given point, you have either a trough or a crest. And I guess at some points in between it cancels out, but otherwise crest, trough, crest, trough. So the length of any instrument is just half a wavelength of sound because we're not getting the full crest and trough like one after the other. So therefore, the length of any instrument is equal to half a wavelength of sound at its fundamental mode. Now, we can force things into higher vibrations, and we call that overtones. So you can force the strings to vibrate even faster and faster and faster. And so when that happens, the wavelength shrinks with higher, as the frequency increases. So increased frequency typically means you have a decreased wavelength. Because after all, the universal wave equation, as long as the medium is constant, the speed of the wave should remain constant. And therefore, if frequency is increased, the wavelength is decreased. So this would be an increased frequency because for the same length of the instrument, we now have two whole wavelengths fitting in the exact same length of the instrument. So in the music world, they tend to call these higher order vibrations harmonics. That's just something to note. I'm probably not going to get into it in this video. That's for another time for you guys. Otherwise, it's just another name for the most part. So there are three cases. This video is going to have case 1 and case 3 because they're mathematically the same, and you'll see why in a minute. Case 2, I'll just save for another shorter video. Case 1, this is a case where you have your instrument fixed at both ends, so that is your string instruments, and the fundamental you've seen already, we know that the length of the instrument is equal to half a wavelength of sound. If you get it to vibrate even faster, the next noticeable resonance point where you actually hear music and it actually kind of makes sense of what you have, typically you'd add on another half a wavelength of sound. You'd increase the frequency until you get another half wavelength fitting in, and it ended up looking like this. So this is where you're going to get another resonance point. Okay, and so when you have the first overtone, you end up with 2 half wavelengths of sound. All right, 2 half wavelengths of the vibrating string, which is, add the two together and you're going to get a full wavelength. You get a full crest and a full trough as it's vibrating. So the length of any instrument in this case is 2 half wavelengths. 2 half wavelengths would be lambda. So you have 1 full wavelength. If you get it to vibrate even more and get to the next order overtone, well, once again, you would add on another half a wavelength. Okay, so now we have 3 half wavelengths. There's half a wavelength, so that would be the fundamental. Here's another half a wavelength, that would be the first, and here's another half a wavelength. This would be the second overtone. So if you add 3 half wavelengths together, the length of this instrument, the length of this string is equal to 3 half lambda, so 3 half wavelengths. So we could go on to the third and fourth and fifth and sixth and seventh overtone, and you probably get the idea that every single time we're just going to add on half a wavelength. So the equation to relate the nth overtone, so any number of overtone, whether it's the fourth overtone, fifth overtone, sixth overtone, you can just create an equation by knowing that the fundamental starts with half a wavelength, and then every overtone after that, you're just adding on half a wavelength again. So if you combine the two together, you should just get the length of any instrument is equal to the wavelength of sound multiplied by the overtone value plus 1, all divided by 2. And that'll give you a representation of the length of the instrument with respect to the wavelength of sound. So applying that to a word problem in physics, in this case, we have a musical string instrument, has a length of, we'll call this 48 centimeters, so yes, 0.48 meters, so it's probably a violin string. The violin itself wouldn't be 48 meters, 0.48 meters or 48 centimeters. That would just be the length of the actual string. So you'd have a little bit of length before and after the string, but this is mainly the length of the string. And in this case, it is vibrating the 7th overtone. So what would the wavelength be for such an instrument? And what frequency is the instrument vibrating at if the speed of sound is 340 meters per second? So this question has 2 parts. First part, identify everything that's given to you. So you know the length of the instrument, or the string at least, is 48 centimeters. But again, I'll leave it as 0.48 meters. The wavelength is unknown to us. It is vibrating the 7th overtone. And part B wants us to find the frequency. And they gave us the speed of sound. So with all that information, we would just pick the appropriate equations. Start off with our first part of the question. We know we have a vibrating string, so we'll use the vibrating string equation for resonance. So lambda multiplied by the overtone value plus 1, all divided by 2, should give us the length of the string. But in this case, we're looking for lambda. So we will just plug everything in and then just manipulate the equation after the fact. So 7 plus 1 is 8, divided by 2 is 4. So if I put that in play, then you just have to divide both sides by 4 and solve. So pretty straightforward. Then you would take your approximately 12 centimeters, but again, leave it in meters, and that's mainly because our speed of sound is in meters. So you want to make sure your units are the same. So when you apply that to universal wave equation, you would plug in your wavelength and manipulate the equation such that frequency is your speed of the sound wave, all divided by lambda. And then just once again, it becomes a plug and play. So half the battle is just trying to pick the correct equation and make sure you know how to execute the mathematics. So 340 divided by 0.12 meters. So sticking with 3 significant figures, because I have 3 significant figures for the length, 3 significant figures for the speed of the sound. So by the time I was done finding lambda, I should have 3 sig figs. If you're concerned, we don't worry about sig figs when it comes to the overtone value, because often it's just a single digit or at most a double digit number. And the 1 and the 2, they're just part of the equation. So we don't worry about the significant figures or the significant digits for those. So that means in the end, I should just have 3 significant figures. So I would just simplify it to, since I'm in 2,833, I would just simplify it and call it 2.83, and then I'd use a prefix for kilo. So that would be my 1,000. You could have used scientific notation if you'd rather, but I'm more of a prefix person. I prefer prefixes. So that's where I would leave it. And then you're done for the day. Obviously, if you left it like this and you wanted to just write it down to the 1,000, I would have called it 2,830 and just rounded that second 3 to a 0. So that's one example. You have, I think, 7 or 8 problems to actually try. And the page looks like this. I don't quite remember what page it's actually found on, but it does look like this. Shouldn't be hard to find. It's the only one that has pictures all over it. I didn't make this assignment, so someone who liked pictures made the assignment. And most kids ask this question, like, how do I do question number 1? That's not like the question that you did in class. I was like, okay, no, this isn't. Question number 1, I'll just say in the video here, all it's asking for you to do is to relate the length of the instrument to the wavelength of sound. So just like the fundamental and the first overtone, the second overtone that you saw earlier in this little video here, you're just trying to relate the length of the instrument to the wavelength of sound. So basically, given the overtone value, so the fundamental, the 5th, and the 34th, you just plug it into the resonance equation, and you try to create an equation that relates the length of the instrument to the wavelength of sound. So you're just trying to get an equation. You're not actually trying to solve it and get an actual wavelength or an actual length of the instrument. You just want to create an equation based on the given overtone values. So that's all question 1 is. Question 2 is more like the problem that we did together in this video. So other types of instruments. So there's lots of different types of musical instruments. It would be a 2 open-end instrument. And for that, for the most part, they're often percussion instruments or some wind instruments like organ pipes or I've been told a bassoon. I've never actually seen a bassoon in person, but when I think of 2 open-end instruments, I usually think of this Blue Man Group and hitting just random objects. So they often turn random things into musical instruments. And I'll just give you a quick little example. Not sure how well this is going to turn out on YouTube. After all, this is a video I took from YouTube just so that I can always have a copy of it. Obviously, I have no rights to this, so, you know, sue me, I guess. So they're just hitting this instrument. Air is able to escape out this hole and this hole. And depending on the length of the instrument, you're going to hear slightly different frequencies. And they're a pretty entertaining group to watch. I'm going to pause it there. And they typically attach on another instrument. You can kind of see where some ticks are in this. I hope it shows up on YouTube, but you kind of can see that they have things measured out already, so they know exactly what length they should need to extend or shorten their instrument to in order to change the actual pitch that you will hear. That guy's got a weird look. I found a good time to pause it. So that's all I'm going to show this video. You can look them up. They're called the Blue Man Group. They're pretty entertaining to watch. And they, again, just turn any instrument, anything. This is just PVC pipe. They can turn anything into an instrument. And they're, again, really entertaining. So this would be an instrument that is open at 2 ends. He was hitting it at some random spot. Air can escape out the front and it can escape out the top part. And it's going to create certain frequencies of sound. So when these are forced into resonance, because that is what's going on, it is resonance, you have a little bit of a different scenario. So it's not a string. So keep in mind your basic waveform looks like this. If we're drawing a crest and a trough, obviously it is a sound wave. So technically it is a longitudinal wave. So it doesn't actually look like this. It's a series of compressions and rarefactions, but that's hard to draw. So by and large, most people just stick with transverse waves. So when it's under resonance, you're going to end up with the wave oscillating back and forth. So from a crest to a trough and et cetera, as it's vibrating back and forth. But if you divide this wave up, so starting from this point here, so this would be the first quarter of the wave. So I'll put a little tick down there as well. This will be the halfway point of the wave. This will be the third quarter of the wave. And this will be one full wavelength of sound as it vibrates back and forth. So you can section them off into quarters. Now, in this scenario, where you have your fundamental frequency, you can see that the node is the dot right in the center. And as it escapes, it's escaping out the ends at a maximum crest there or a maximum trough there, and likewise out the other end. And that's where you're going to get maximum sound at maximum constructive interference. At the very center of the instrument, In this case, that's where the note is. So that's where you have destructive interference. So in order for this to undergo resonance, we have to have maximum sound coming out at constructive interference. So what we see here is if we erase this wave in the top right here, so if I remove 1/4 of the wave from that end and remove 1/4 of the wave from this end, we're left with half a wavelength of sound. And so that is the relationship. The length of this instrument is equal to half a wavelength of sound, right? So that's what you're going to get at the very lowest frequency when you're like the guys in the video pounding on these pipes. Organ pipes would be the same idea, except you might have a hole here or something, and you're forcing air out this way, and air will, or you're pushing air into that maybe center part here, and then air will escape out the left and the right and the left, and you're going to get resonance. So if you can force it to go out faster and increase the frequency, you're going to change the pitch of it. You're going to change the wavelength, so you'll shorten the wavelength of sound. And so, of course, that's going to change your overall frequency. So in this case, the length of the instrument, so if we look at this, it still escapes with a maximum. So that's the important thing, the important takeaway here is you escape at a maximum. So just like before, we have to the right, in the orange, we have 1/4 of the wave on the right, and we have 1/4 of the fundamental wave on the left, and those are still part of the first overtone, right? We still have the overall 1/2 that we had in the fundamental, but we added on half a wavelength of sound. So now we have this loop, antinote, if you will, in the center. So we added on half a wavelength of sound. So just like the string instrument, we added on half a wavelength, and now the length of my instrument is equal to 2 half wavelengths. So 2 halves is equal to a whole, and that lambda looks terrible. I'll draw it again. 2 half wavelengths equal a whole. So we have a quarter here, so 1/4 of a wavelength here on the left. We've got a 1/4 of a wavelength on the right. 2/4 is equal to a half and a half is equal to a whole. So just like the string instrument, when you went from the fundamental to the first overtone, you added on a half a wavelength. So again, just like the string instrument, when you go to the second overtone, you're adding on yet another half a wavelength. So now you've got 2 loops in the center. Right, you got a loop there, you got a loop there. I can't draw to save my life. So now you have 2 half wavelengths in the center. So now we have a full wavelength in the center, right? Starting from this point here, you got a wavelength crest going up, trough going down, and you got 1 full wavelength in the center. You still have the 1/4 wavelength there. You got the 1/4 wavelength on the other end. And of course, it's going to escape out your instrument at a maximum constructive interference. So we're adding on another half a wavelength from where we left off, which means the length of this instrument, the second overtone, is just like before, is now equal to 3 halves lambda. So mathematically, it is identical to the second overtone of a string instrument, but physically, it is doing something completely different. Right? It is doing something different than the string instrument. It's still vibrating. It's still vibrating the air, whereas before it was vibrating the string, but the air is vibrating just slightly different. All right. But of course, mathematically is identical. So if it is mathematically identical so far, then we can just go on keep going one step further and more or less come up with the exact same equation for our string resonance. All right, so mathematically identical, physically different. So mathematically, we'd kind of treat it the same. We'll do a different problem here with an organ pipe. We know an organ pipe would be open at both ends because I think I've said that at least once or twice now in this video. So this question says, it is desired that the second overtone of an organ pipe, so therefore open at both ends, be 5,000 hertz. So we're building one, I guess. How long must the pipe be if the speed of sound is 340 hertz? So it's the same speed as the last question because we're not trying to change this too differently. State what you know. You know it's the second overtone. You're given the frequency and you're given the speed of sound. We're looking for how long must the pipe be. So we're looking for the length. So if we look at the equation given to us, right? There is no frequency, there is no speed of sound in the equation that relates the length of the instrument to the wavelength of sound. So we have to do an extra step in between. So we need to find lambda, and therefore we use the universal wave equation. So most of the time I would just take this equation here for lambda, once we have it manipulated, and just substitute it in here. But for the video, I didn't do that. But often I would just do that in there, and then I only have to grab my calculator once. But in this video, I didn't do that. So what I would do is I would actually plug in the velocity or the speed of the sound. So 340 divided by 5,000. Now 5,000 has an underline under that zero. So that's an indication that we just have three significant figures. We have an underline under this zero. So that means that's also just three significant figures. So if we do a little bit of math there, 340 divided by 5,000, that should give you about 6.8 centimeters. All right, I left it in meters there, but odds are good. I'm just going to probably want to use centimeters from this point on, because after all, in the next part of the equation, I just have two lengths. So whatever my wavelength is, if it's in meters, I'll leave my length in meters. But if I put this wavelength in centimeters, then my length will be in centimeters. So since I'm dealing with a small number, I'll just change and use a prefix and just use centimeters from this point forward. So therefore, my wavelength is 6.8 centimeters. I'm in my second overtone, so where n is, I'd put the number 2. So 2 plus 1 is 3. 3 divided by 2 is 1.5. 1.5 times 6.8 will give you 10.2 centimeters. So it's not an overly long instrument, but again, we are at 5,000 hertz, so I would expect it to be pretty short. So that's just an example of how to do open at both ends. So very much similar. In fact, I would say that the methodology is the same as a string instrument. So there's not a whole lot going on different mathematically. It's just the physically what's happening that's different when it comes to mechanical resonance and instruments. So when it comes to two open ends, there's a different worksheet to give it a try, but it's more or less the exact same idea as the string instruments. So question 1 is the same. You're just trying to find a length uh, uh, of the instrument with respect to the wavelength of sound. So again, it's just a matter of figuring out what the fraction is here in the multiplier for the fundamental, the fourth, and the 45th overtone. After that, everything else is more or less the same and very similar to the two questions I did here in this video. So on that note, I'm going to stop this video here because it's getting pretty long, and I'll make a separate video for the wind instruments. So if you have any questions, just send me an email and I'll get back to you as soon as I can.